Welcome back. Right, so that's our fourth lecture on error analysis in biology. Let's start with a quick reminder of what we did last time. So I talked to you about confidence intervals mostly, and I will keep talking about it today. Confidence interval is a sort of a probabilistic measure of uncertainty, and specifically a 95% confidence interval. In repeated experiments, the true parameter that you are trying to measure will be within 95% of your repeated experiments. That's the meaning of this. And generally, it's better than the standard error. It makes more sense if you quote it. I told you about sampling distribution, which is key to understanding confidence intervals. It's basically a distribution of a sample statistic, for example, the mean. You calculate sample mean, you calculate it again, you're resampling many times, and you can build this sampling distribution of the mean. Of course, this is purely hypothetical. You can't do it in real experiments, but you can do some calculations on this. And for the mean, for the sample mean, there exists a transformation which turns this not quite well-known distribution, we don't know its width, into something which is very well known, and you can make calculations, and you can find this confidence interval by rejecting 2.5% on each side and leaving 95% of samples here. And then you take this t star, this is the critical value from t distribution, and you find the confidence interval on the mean. So this is fairly simple. Then I tried to explain your confidence interval on the median, and I noticed from your feedback that probably it wasn't done very well. I will try quickly do this again, maybe from a slightly different approach. So I think the most confusing thing here was that for the median, we do not build a sampling distribution. We operate directly on the median distribution and do our calculations there. So instead of that, we draw just one sample of n points and look at probabilities. So we draw this one by one. Now, the very fundamental property of the median, of the population median, is that if you draw one point at random, if you do one random measurement, then you have 50% probability that it is less than the median and 50% probability that it is greater than the median, because median divides every entire population into two equal halves. So we can use this. And imagine an experiment where, okay, we can come back to our mice. You have a population of mice where the median body weight is 20 grams, and you draw a sample of 8 mice. You weigh them, and you get 8 numbers. So the true median is somewhere here, and we have 4 numbers which are less than the median, 4 numbers that are greater than the median. And if you look at this process of drawing one mouse from the population after another, with every mouse, you have a 50-50 probability that it will be on the left or on the right on the median. So that probably resembles something, a very simple experiment which would correspond to what we do here. And it's basically tossing a coin, or 8 coins in this particular case. So if you draw a mouse, it's 50-50 probability, left or right of the median. If you toss a coin, you have 50-50 probability, heads or tails. So we can say, if it's heads, then let's say our number is less than the median. If it's tails, our number is greater than the median. These are two experiments which correspond to each other directly in probabilistic terms. And I explained to you in previous lectures that this leads to a binomial distribution, and you can calculate probabilities. So probability of having this configuration of heads and tails is 0.27. But you can have a different result of your experiment. You can have 7 mice which are heavier than the median and 1 which is below. That would correspond to having 7 tails and 1 heads, and probability of this is much lower. It's about 3%. So you can build this probability distribution, which is a binomial probability distribution, and you can do some calculations directly on this and cut the probabilities you request. So what you want, as usual in this case, for example, for this sample, you might say, okay, our best median estimate is here, and we want to cut off 2.5% of this probability distribution on each side. The problem is, these are individual probabilities for each bar, So this one is 0.004, but this one is 3.1%, and you want to reject 2.5. So you can't reject 1 or 0. You have to do it somewhere in the middle, in between. So basically, you would need to interpolate between these numbers and then interpolate between these numbers. There is an exact method to do this interpolation. It's a little bit complicated, so I didn't show you this. It's in this paper. You will have handouts available. You can come back to this and read this if you wish. What I showed you was a very simplified method, which still gives a very good approximation of the confidence intervals on the median. So you can use either of them. I presume any good statistical package should be able to use this method, and you can find confidence intervals on the median. I just wanted to show you where they come from. So let's continue with our confidence intervals, and I will show you how to calculate them for other estimators. Let's start with count data, okay? In a sense, it is a little bit similar to the median. We do not build sampling distribution. We do just very simple calculations here. So if you remember from previous talks, if you have a count, for example, you count colonies on a dish, and you can say, okay, there is 5 of them here. So standard error of a count, C, is square root of this C. So for this particular sample, after proper rounding up these numbers, you can say that this count is 5 plus minus 2 in terms of standard errors. But we want to do better. We want to do, again, a probabilistic interpretation. So we want to find a confidence interval on mu, which is the Poisson mean count of the entire population. Now, again, like in the median, there is an exact method. It's described in this paper. It's even more complicated. It would take me probably half an hour just to explain this, so I have to skip this. But again, there is a really good approximation which is perfect for any practical use. So the idea is that you take Poisson distribution, you do some cutting and reversing probabilities, and then you use chi-square distribution and so on. It's a little bit complicated, but you can do it this way. And this is perfect for practical applications. So you have your count. It's, let's say, 5. First, you have to set this critical value Z from the Gaussian distribution for the given confidence level. Basically, it's a value that cuts off given probability within standardized Gaussian distribution. So, for example, for 95% confidence, this is 1.96. You probably remember this number. That means that if you are from the mean plus minus 1.96 standard deviations, you will have 95% of probability within this region. So this is just a number to remember. And then for a given count, C, you calculate these simple equations, and they will give you lower and upper limit on your count. So it's count minus Z times square root of C plus Z squared minus 1 over 3. That's the lower limit. And count plus Z, this time C plus square root of C plus 1, Z squared plus 2, divided by 3. Okay, they are not really complicated. Look at this example. If C is 5 and we take 95% confidence interval, so it's 1.96, you use these equations, you find the lower limit is 1.6, upper limit is 11.8. It's quite high. And if you round it up and write down like this, your result will be 5 plus 7 minus 3. This is how you denote asymmetric errors. This error is the upper limit is bigger than the smaller limit or smaller error. So this is standard error plus minus 2. This is 95% confidence interval on this count, and it's plus 7 minus 3. Now, this is just to show you how well it works. This is an example of count, which is 5 as an example. This is our standard error. This is the exact confidence interval calculated using this exact method. And this is our approximation. As you can see, they are very, very similar. And this is the same for count of 30. One thing you should notice here that for small numbers, or even not very small numbers, this error bar, this confidence interval is really huge. So 5, it ranges from 1 to almost 11, and even for 30, it's about plus minus 12 or so. So every count is rather uncertain in this sense. You might wonder one thing here. I told you that the confidence interval on 5 is from 1.6 to 11.8, but shouldn't this interval be integer? You can think, all right, it's 5, so it's a number. Clearly, if it's 1.6, this 5 cannot be less than 2. It's either 2 or it's 1. Yes, it's a count. You can't have a non-integer count. So maybe this confidence interval should be integer. Well, not quite. That's because you need to understand the confidence interval itself. It's a confidence interval for the true mean. It's not a confidence of this number. It's confidence, basically it tells you that this interval, it indicates that we expect the true mean to be in this region with a certain confidence. And if you remember, this is an example with radioactive decay I showed you before. You have counts which you can measure in time bins, and you have 2 counts here, 0, 1, 3, oh, that's actually 6, and so on. So count is integer, but the mean of this process, the mean count is 3.5 counts per second. This is a real number, and by building a confidence interval, we limit this real number. So the confidence interval itself is also a real number, despite count being integer. The next thing I wanted to show you is confidence interval of the correlation coefficient. Right. So if you remember, well, one of the ways of calculating correlation is using Pearson's correlation coefficient. There are a few other ways, but I will concentrate on this one. I showed you before how it works. So for pairs of points, xi and yi, which are presented in these diagrams, you can calculate correlation coefficient. And when points are correlated, it's a larger positive number. When they are uncorrelated, randomly distributed, this is around 0. And when they are negatively correlated, it's a negative number. And you can say, okay, here correlation is 0.89. These data, whatever it's shown here, these are correlated. Our samples are correlated. But really, even if you find correlation coefficients which is large, in biological terms, 0.7, 0.8, 0.9, you probably consider this a good correlation. It doesn't necessarily mean that these things are well correlated. Well, what you need a confidence limit on this correlation coefficient, or alternatively, significance of correlation to show that it really is true correlation. So how do you do this? Well, we go back to our sampling distributions, and we do another Gedanken experiment, a thought experiment. So imagine a population of pairs of numbers, an infinite population, we have lots of numbers, and this population internally has a correlation of 0.73. Again, thought experiment. Normally we don't know this. And what we can do, we can draw a sample of, let's say, 30 points or 30 pairs of points, calculate correlation coefficient, put it somewhere in this graph, and do it again and again. And of course, due to random sampling, every time you draw a sample like this, your measured correlation would be different. And from this, you can build a distribution. It's a sampling distribution. Again, we did it before for the mean. This is sampling distribution of a correlation coefficient. As you can see, it peaks somewhere here around 0.73 or close to it, where the true correlation is. And it's rather asymmetric. It's got a long tail. So there are quite a few samples occasionally which give you very, very low correlation, despite the population being quite highly correlated. So you have this sampling distribution. Unfortunately, it's really not very well known in analytical form, especially we don't know its standard deviation. But what we want to do is the same as before. We want to cut off 2.5% on each side and leave 95% of samples inside this distribution. And that, ideally, that would be our confidence interval on the correlation coefficient. But since we cannot do this directly, we can do a transformation. And this is something that Fisher did. He developed this transformation. It's called Fisher's transformation. You just calculate a new statistic called Z. And it's a very simple formula. It contains only R. You don't even need to remember, you don't need to know your original pairs of points. All you need to know is R. And you can use this Z and build a sampling distribution of Z. This is a standard approach. So instead of building sampling distribution of our R, correlation coefficient, for each sample, from our thought experiment, we calculate this Z and build a distribution of Zs. And this distribution has a very nice property. It's Gaussian, and we can find its standard deviation. It's 1 over square root of n minus 3, which allows us to do our probability calculations, because within the Gaussian distribution, you can cut off 95% easily if we know the mean and the standard deviation of this distribution. Here's an example how you can use this. So imagine a sample of 30 pairs of numbers, and the correlation coefficient for this sample calculated, that's what you get, is 0.73. So you use this transformation. You calculate Z, and if you put this in here, you can quickly find it's 0.929. You calculate sigma, 1 over square root of n minus 3. N is 30, so it's 1 over square root of 27. It's about 0.19. And because Z is normally distributed, okay, what's the number? What's this magic number? How many standard deviations do I need to cut off 95%? 1.96, exactly. So if I know Z and sigma, all I need is to find this limit, Z minus 1.96 sigma and Z plus 1.96 sigma, as illustrated here. This is our Z, Z lower, Z upper. This is our required 95% of confidence. It's in here. And once we have Z lower and Z upper, we can go back to our original distribution and basically take this equation, solve it for R, reverse it. R is this way. And you just take your Z lower, Z upper, put it in here, and you will find corresponding limits on R, on the correlation coefficient. And if you do all of this, you will find that the lower limit is about 0.50, upper limit is about 0.86. Again, this confidence interval, and you can see it even here, it's asymmetric. It's got this tail here down there, and you can write it down as 0.73 minus 0.23 plus 0.13. This is the way to write it. And that's a 95% confidence interval. Okay, another example here. So these are the numbers I just calculated for you in the previous slide for the sample size of 30. What happens if you have only 6 points and calculate correlation? So what is Z here for 6 points? Quickly. It's there. Well, look, it does not depend on n. It's exactly the same. Yes, the same. Sigma, well, you can quickly calculate it. It's 0.577. Then you find lower and upper limit on Z. And you see the sigma is, well, this is the same, but sigma is much wider, so it builds a much broader distribution. And from this, if you calculate this and put it in here, you will find your lower and upper limit on correlation coefficient minus 0.2 and plus, well, 0.97. So it's basically everything. It includes something which is not correlated at all because 0 is within confidence interval, and it goes up almost to 1. So you would write it down like this. Yeah, you can do this, but in practice, it means that there is no correlation. Though you might think that there is, because you take a sample and you calculate it. It's 0.73, except that it's not significant at all. And this is a little bit outside of the topic of this lecture, but I will quickly show you how to find significance of a correlation. And so the null hypothesis here is the sample is drawn from a population where there is no correlation at all, and you want to find probability that you observe such huge correlation as in your sample. So what you do, you calculate this statistic. It's called T, R times square root of n minus 2 divided by 1 minus R squared. And it's called T because it follows T distribution with n minus degrees of freedom, so you can find your probabilities. And the p-value would be the probability of getting the observed correlation purely by chance. And in our examples, this is 30 points, correlation 0.73. These are our confidence intervals, which I calculated for you. The p-value here is about 10 to minus 6. If you do exactly the same for just 6 points, the p-value is 0.05. So if you have 6 points and repeat this experiment many times, 20 times out of 1 in 20 would give you absolutely no correlation. So this is not really significant, and it's expressed either by this p-value or by the very wide confidence interval. So if you calculate a correlation coefficient, please find, well, the best is to find confidence intervals on this, because it will always tell you what it is, really. Right. The next thing is a proportion. So we have median, count, correlation, proportion, lots of things you can find errors on them. Now, proportion is, well, it's a very simple thing. It's a number of successes divided by the sample size. So if you have several trials, you can call it a success or a failure, and you have then fraction or proportion of successes. Basically, it's you do your count of things and find a fraction of things that have the required quantity or whatever you are looking for. For example, poll results, 32% of voters can vote party X or whatever, so that's just a proportion of entire electorate. Survival experiments, for example, 3 out of 10 mice can survive after, I don't know, 5 or 10 days. Counting cells with a given property and so on. Anything that you count could be done this way. And sample proportion, which I denote here as p hat, with this little hat on top of this, just to make difference between the population proportion. So sample proportion p hat is an estimator of the population proportion p. So again, we have the same thing. There is some unknown population with unknown true value, and we are trying to find confidence intervals on this. And if you look at this experiment, so thought experiment again, you can take 10 mice, then you infect it with something nasty, as you do, and then apply some sort of a treatment, and then watch the poor creatures die. And of course, so you start with a proportion of 1. You have all your mice in the beginning, and then you have fewer and fewer, and eventually, after about 15 days, you have no mice left at all. This is a survival curve. You have seen it many times before. But the survival curve by its own, it's not worth really much. You need error bars. You need error bars here. You need to know how uncertain this is. Okay. Well, a sampling distribution is useful, again. So we do another Gedanken experiment. And now let's consider a population of mice where 13%, this is our population proportion, are, let's say, they are immune to a certain disease. So if you draw your sample of 10 mice, within this sample you might have, for example, 3 immune mice, or 1, or 0, or 5, depending how lucky you are. And every time you do it, you find a new estimator of this population parameter, of this unknown parameter. If you repeat it 100,000 times, and this is a computer simulation, you can build, again, the sampling distribution, this time, of a proportion. And it looks like this one, or this one, or this one, depending on the sample size. So this one was calculated for a very large sample of almost 1,000. And as you can see, it's quite narrow. The proportion in each sample is tightly concentrated around these numbers here. But more in a real biological world, if your sample size is 10, you have this very wide distribution, this red curve, which extends from 0 to, well, much higher than it goes outside this figure, actually. So depending on the sample size, the width of this sampling distribution will be different. Now, you tell me, what kind of distribution is this? So a hint is every time you draw one mouse from your population, it can be either immune with probability p or not immune with probability 1 minus p. What does it remind you of? It's a binomial process. It's a binomial distribution. So you can call immune mouse, it's a success with probability p. Not immune is a failure. So lots of trials, and there are failures and successes, so which is good. That means that this distribution is known, and we can do some calculations here. We have to do a little modification first. So binomial distribution, as I presented this to you before, is usually presented in terms of absolute numbers. So if this is a binomial variable s, then p of s equals k is a probability of having k immune mice in a sample of n. And I showed you before that this leads to a binomial distribution where mean is np, so n is the sample size, p is this intrinsic probability, and this is standard deviation. However, here we don't have absolute numbers. We deal with proportions. So we need to do a very simple scaling, which is going to change these numbers very slightly. So we need to create a new random variable. I call it theta, or phi actually. It's s divided by n. We scale it to a proportion. So this variable is not an absolute number, it's a proportion. So there is a probability that this equals k over n. It's a probability of having a proportion of k over n of immune mice in a given sample. Now, if you scale a random variable by a constant, its mean and standard deviation will scale in the same way. So this is very simple. We divide it by n, so this mean, np, will be divided by n, and you have p, and this is also divided by n, and this is the new standard deviation. So this is the standard deviation of the distribution of a proportion, and this is the quantity we really need, okay? This is basically the width of the sampling distribution, and you know from previous examples that the width of the sampling distribution is what we are after, and from this we can find confidence intervals. So we need to know this number. We have to do something about it. Right. Well, you don't know p because it's a population parameter, but that's just a reminder from previous lecture. I did a very similar calculation for the mean and standard error of the mean. So I showed you that if you build a sampling distribution of the mean by calculating lots of means from samples, the width of this distribution is expressed by this simple equation. It's the population sigma divided by the square root of n. But we don't know sigma, so what we did, and this is a standard trick in statistics, you replace unknown population parameter with a known sample estimator. So you replace sigma with standard deviation, and what you find is the standard error. So this standard error, this estimator, it estimates the width of the sampling distribution. And we do exactly the same thing here. We have our initial formula for the standard deviation. We replace population parameter with this p hat, that's the observed proportion, and what we get is the standard error of the proportion. This thing estimates the width of a distribution. So it's very nice, and it's quite often used in practice, except that it doesn't work very well when the number, the proportion, is close to 0 or 1, when it's extreme. You can even see it here. This red distribution is quite broad, and if you calculate some estimator in the middle, plus minus standard error, it probably would give you negative numbers as well. The proportion, the way it's distributed, it requires some tweaking, and it's done this way. So one of the approaches is called a Wald method. It's a modification of this standard error of a proportion, which gives you very reasonable numbers. That's an empirical thing, and you start with a sample of size n, where you have s hat successes. This is our estimator. And then you select a Gaussian number z for a given confidence. Again, let's choose 1.96 for the 95% confidence interval. Now, what you do now is you calculate corrected quantities. So you take your original number of successes and correct it by this number, z squared plus 2, over 2. And then you calculate a corrected number of points. So you tweak them, and you add z squared to this, and then calculate a corrected proportion. So you take this divided by that, standard error, and then you calculate confidence intervals by multiplying this by z. I think it's best if we look at an example. Consider a sample where you have 10, for example, mice, and there is one success, one surviving mouse, for example. So the proportion is 0.1. It's quite obvious, yes? And if you calculate just standard error, uncorrected error expressed by this formula, if you calculate it directly, what you have, this standard error will be 0.1. So you can say that proportion is 0.1 plus minus 0.1 standard error. But this is not a very good result, actually. And if you do corrections, you will see it. So using these equations, the corrected number of successes here, or mice alive, is about 2.9, and the correct n is about 13.8. So now the corrected proportion is 0.21. The corrected standard error, this one, is still very similar as 0.11, but this is shifted towards higher numbers. So these corrections, what they do, if you have your proportion somewhere in the middle, about 0.5, this correction won't do anything. If your proportion is either very low or very high, the correction will shift it towards the center. So it kind of removes the extremes. And from this you can find the margin, which is called margin of error. So you multiply this thing by z, the assumed z, and this is the size of the confidence interval. And confidence interval would be this p, not our original, but the corrected p, plus minus this. So it's from 0 to 0.43. You probably have heard about margin of error when proportion is considered, well, from newspapers, because every time you read about opinion polls, there will be a number of voters, following one or another party, and sometimes they will tell you that the margin of error is, for example, plus minus 3%. So what they mean, mostly, they don't explain it, but usually it's this thing. It's a 95% confidence interval. So if you have opinion polls and it gives you plus minus 3% interval, it's probably this. And this 3% comes, if you do these calculations for a sample size of 1,000, that will give you about plus minus 3%. So a typical opinion poll would include 1,000 people and typically would give you plus minus 3% confidence interval. So we can now add error bars on our survival curve, and you can see it strongly depends on how many points you have. So if you have only 10 mice here, then these error bars are quite substantial. You see here, this one is really large here. For 100, it's much better, but still there are significant error bars. One thing you need to notice is that even if your proportion is 0, even when all your mice are dead, there are still some mice here, within error bars. There are sort of undead, I don't know, zombie mice, basically. Which means that if you repeat this experiment many times, occasionally, after 15 days, you can still have mice surviving. So that's your virtual mice. Yes, definitely it's always better to have a control. This is just a simple example how to estimate error bars on these numbers, but yeah, you would have to normalize it to a control, and then it becomes a little bit more complicated. But these error bars, this is a confidence interval, so it tells you that within 95% of repeated experiments, the true proportion will be somewhere there. That's all. It's purely statistical. Let's do a little experiment with you. I will stop it for a second. And so, as you know, well, there are some left-handed people probably here, if they admit to this. We can calculate proportion. So there are 70 people here. Who is left-handed? How many? All right, let's see. 1, 2, 3, 4, 5, 6, 7, 8. Once again, 1, 2, 3, 4, 5, 6, 7, 8. So our sample size, right, so first of all, in general population, there are about 11% of left-handed people. That's what I found on the internet. Sample size here is 70. There are 7 left-handed people. So we have Z of 1.96. This is the corrected proportion. So the real proportion is 10%. The corrected will be about 12. And the confidence interval of this is from 5% to 20%. It's quite large. You are a small sample, unfortunately. So we cannot constrain it any better, but you can see that the population mean is well within our confidence intervals, which is good. You are probably a representative sample. Well, you are small. Right. Now I will diverge a little bit from confidence intervals and tell you a few words about bootstrapping, which is a very nice and versatile technique which can be used for many purposes, but it can be also used for finding confidence intervals in case where your estimator is very complicated and you can't do anything with it. You can also use it for power calculations. So what we are trying to do here is to approximate sampling distribution from just one sample. So instead of doing a Gedanken experiment where I have infinite sample, I have only one measurement, one sample in n replicates, and that's it. And I'm trying to do something about it. And this is a sample here. There is 12 points here. Could be our mice. The mean of this sample is 18.6. This is our original sample. Now what I'm going to do is resampling, random resampling with replacement. What it means. So if you had little balls with numbers on them, one ball with this number, another ball with this number, and so on, you put them in a box and you draw one of them at random and you find a number 27.7. It's this one. Then you put it back in the box. So when you draw another number, you have chances of drawing again the same number. And you can see it here. This is our random resampling with replacement, because we drew this 18.2 twice. Twice. So if you do this resampling once, you will get this sort of numbers. These are the same numbers, but they are reshuffled, and some of them are repeated, some of them are missing. So obviously the mean at the end will be different than the original mean. And if you do it again and again, every time you'll get a different mean, and you can build a distribution of these means. So I calculated 1 million times. It's quite easy to do in a computer. And this is the distribution you get. So this is not a sampling distribution. This is a bootstrap distribution. It's calculated from just one sample. And this thing approximates, or it tries to approximate the actual sampling distribution. And once you have this, it's very easy. You have all these million samples, so you cut top, what is it, 25,000. You cut bottom 25,000. And what you have here is then 95% confidence interval. And if you do this, you will get this result from bootstrapping. For comparison, this is the confidence interval calculated from t-distribution in a just classical way, as you do for the mean. It's slightly bigger, but they are not, very much different. So you could potentially use this technique. Of course, if you want to find confidence interval of the mean, you don't have to do this, because there is a very simple method, analytical method to do this. But for more complicated things, it's sometimes useful. So bear this in mind. This method becomes useful. Okay. Now, now I want to tell you a few words about replicates and choice of replicates, number of replicates. So, as you know very well, replication is the repetition of an experiment under the same condition or conditions. And typically, this is the only way of estimating measurement errors. Using replicates is the only way of estimating measurement errors. So you really need replicates. And just to reiterate it, I will say it again. You need replicates, okay? When you come back to us with some data, please do have your replicates. And then you might ask, well, how many? Right? And that's what biologists ask us quite often. And unfortunately, the answer to this question is not simple at all. So very roughly speaking, there are two cases where you can consider how many replicates you need. The first one, if you measure something, a quantity, and want to estimate its uncertainty or variability, and to get the uncertainty to a certain level, you need a certain number of replicates. And the other thing is when you compare groups or conditions, basically when you do some sort of differential analysis and you need to do power estimates, whether your sample size is good enough. So the second thing is completely outside of the scope of this talk, but I will mention this about uncertainty. Right. So this is a little bit of a busy graph, but let's go through this. What I'm trying to show here is the effect of number of replicates on your final result. Let's consider a population again of our mice. Mean is 20 grams, standard deviation is 5 grams, and we do random draw one by one and increase our sample size, increase number of replicates. So if you have only one replicate, that's our first measurement, which is maybe 21 grams or so. That doesn't tell you anything about uncertainty or variability. If you increase and add 2, 3 replicates and so on, well, the first thing you can calculate is the mean. So this broken blue curve here shows the mean of all replicates from the first one to the given one. So it's a cumulative mean. So for example, if you do 3 measurements, and if you do experiment in 3 replicates here, the mean is this one, and this is plus minus 95% confidence interval calculated for these points. Here, for 2, it's so large, I couldn't squeeze it. I would have to be much bigger plot. It goes from here to very, very high there. So if you have very small number of replicates, of course, it's all very uncertain. But then, with increasing number of replicates, your error, your 95% confidence interval, well, it kind of gets smaller, but it's very wobbly. It can get smaller and then larger again and so on. And this is for one particular sample. You do this experiment again, these curves will look different. They will be kind of very jagged. The only general thing you see is that with increasing number of replicates, your error is getting smaller and smaller, but not very much smaller. So there is a dramatic decrease here from 1, 2, or 3 when you go up to maybe 6 or 10 replicates, and then it's much more gradual. So if you ask me whether you need 3 or 6 replicates, we will always tell you at least 6. But if you ask us whether there is a difference between 20 or 30, maybe. It's not that clear. If you ask a physicist, they will always tell you use 30 replicates. Unless it's Nick, he will tell you use 1,000. Now, there is a very simple method, very simple calculation, which will give you an estimate of how many replicates do you need if you want to find a mean with a certain precision. Okay? So this is how it goes. We go back to our sampling distribution of the mean, which is built from various samples. And if you remember, the width of this distribution is expressed by this equation. It's population sigma divided by the square root of n, where n is the sample size. So I'm doing just rough estimates. The interval, which is twice that size around the true mean, contains about 95% of samples. This is Gaussian, so that will be 1.96, but let's say it's around 2. So let's call this interval, the twice of sigma m, let's call it precision of the mean. Now, this is not confidence interval, this is not standard error. There is no sample here, there is no data. This is only a theoretical calculation using some probability distributions. So 2 times sigma m is 2 sigma divided by square root of n, and this is our precision of the mean. What this equation here, what it's telling you, that if you have a population with a given sigma standard deviation, and you take a sample out of this of size n, this is what sort of error on the mean you are going to expect. This is the precision or uncertainty of the mean on average. And it depends on n as 1 over square root of n. So if n is larger, obviously, this uncertainty or precision of the mean will be smaller and smaller. So we can use it and ask, what sort of n do we need to get a given precision? So the sample size, to get the required precision, you just find n. You solve this equation for n. It's 4 times sigma squared divided by epsilon squared. The unfortunate thing about this is that it requires a priori knowledge of sigma, of population standard deviation, which is not always easy. You can do a pilot experiment to estimate it. Sometimes you deal with data, I don't know, like in proteomics, where you know how these distributions look like. So you can get some idea of the width of your distribution. And if you have this, you can estimate the sample size, which is required. So here's an example. Go back to our population of mice. Let's assume that the standard deviation of the population is 5 grams. And let's assume we will require a precision of plus minus 2 grams in terms of these 95% of samples. So if you plug it in here, it's 4 times 5 squared divided by 2 squared, it's 25. So to get this sort of precision, you need at least 25 mice to get the precision of the mean. Now, because this depends on 1 over epsilon squared, that goes down very quickly. So if you want to decrease this error by factor 2, your requirement on n will grow up by factor 4. So if you want error of plus minus 1 gram, you would need at least 100 mice. So that escalates very quickly. That's a very, very simple thing for number of replicas for the mean. Okay, and I think that's it for today, and I will see you next week.